air traffic control, air defense, and other complex systems require generation of response actions based on the information about the objects in the surveillance area. Information about an object population is typically obtained by artificial sensors, such as radar, and presented to a human operator in the form of a geographic information system, including positions of individual objects and their velocities. This information is then used by the operator to assess the situation and generate a response. However, real-life situations may be way more stressful than in this example. Consider the following. In this scenario, there may be too many objects to display adequately, let alone comprehend by the operator. Therefore, the operator's ability to assess the situation can be compromised, undermining the likelihood of reaching the system's objectives. How could we address this issue and provide the aid to the operator? One way is to formalize calculations performed by the operator and execute them automatically. What does the operator actually want to know? A simple example could be counting objects. How many objects are there in this surveillance region? The answer is 50. This, however, may not be a good description of the situation, since changes in objects' locations within the region and their directions would not make any difference. Look at another situation. This one is strikingly different. Although the object number is the same, many objects in the east are now heading towards the same area or point, and this might be a huge difference to the operator. Suppose that the operator wishes to protect a valuable asset in the area where these objects are now aiming. In this case, the objects may pose a serious threat to the asset. Here we conclude that the operator tries to evaluate the level of threat posed to the asset. In this scenario, the level of threat is perceived as high, whereas in this one, the perceived threat level is low. What distinguishes our work from other algorithms on threat assessment is that we supplement the perceived threat level estimate with a measure of its quality linked to the quality of observations. Provided that estimation quality meets the system's requirements, the estimate can be accepted as the actual value of perceived threat and can be used to generate a response. Importantly, this quality measure is suitable for steering the sensor management process and can be used in development autonomous systems. Operation of the developed algorithm can be demonstrated on a simple example. We consider a situation where a protected asset is located in the center of surveillance region. Over the course of scenario, objects will be appearing and disappearing from the region. The solid black line on the right represents the real number of objects. The objects will generate a certain level of threat. Its ground truth value is plotted against time in the bottom right corner. In the course of time, we are able to estimate the perceived threat level. Together with this, we are providing a confidence interval that is an indicator of quality. This quality may be satisfactory for generating some actions and may not be satisfactory for others. This work is a timely result contributing to the needs for situation assessment in the circumstances when the number of objects in populations is ever increasing and the systems are seriously undermanned. Performance of such algorithm, though, will be strongly dependent on our knowledge about the rules of threat assessment. To develop the algorithm towards an operational capability, a closer interaction with operators and threat assessment specialists is required.